now let's discuss induction. So the inductance can be introduced. Say we have two loops instead of a single loop. So here, say that we have a current running in the first loop. Then this current can produce a magnetic field, and this magnetic field can penetrate the other loop, and the second loop will have a flux enclosing this loop. And if there is a change of the current of loop 1, then it will change the B field, and thus changing the flux of loop 2, and thus because the flux of loop 2 is changed, then there will be an additional EMF introduced onto the loop 2. So you can sort of imagine that if I increase the current on loop 1, this will induce a current running on loop 2. So this is sort of you can sort of already see that in some of the examples earlier. So say that the hot pot cooker by using the magnetic induction. So we have a loop of currents running on the bottom, and it can induce some eddy currents running on the top, and it's a similar idea. So here we can exactly calculate the magnetic field produced by the loop 1 using the Biot-Savart law, even though it's typically a complicated calculation. But in principle, we can get the flux passing through the loop 2 by calculating loop B1 produced by loop 1, and then do a surface integral. So the flux phi 2 is, you can see that if you plug in this B1, it's proportional to the current. So now if we put the proportionality here and include everything else into this M21, then we can have a linear relationship. So the larger the current on loop 1, then the larger the flux on loop 2. So then this M21 is called the mutual inductance of the two loops. So it's the proportionality of the flux over the current. So I don't know if you remember a similar analogy before, earlier when we discussed the electrostatic case. So we have say that if we have a parallel plate capacitor with charge Q difference, and we can also calculate the voltage. So the voltage and the charge Q also has a linear relationship, and it has a constant called capacitance that relates the charge Q and the V. Here this mutual inductance is of a similar idea. Now instead of writing this B dot dA, we can also rewrite the magnetic field in terms of the vector potential for that magnetic field, which is del cross A. And using Stokes' theorem, we can convert area integral to a linear integral. So that can convert to A dot dl. And then this A dot dl is the A1 is something that we already calculated in the chapter 5. So you can look at the lecture 14, page 3. So the equation is the A1 equals to the mu naught I1 over 4 pi times the closed loop integral of dl over, I guess that should be that could be a separation vector. I'll double check. and from this expression for this A1, if we plug that in, then this single integral becomes a double integral, where the integral runs from the where the integral is integrating over dl1 and dl2, where the L1 and L2 here they are the two line elements, and here the separation vector is the from dl1 to dl2. Here this should be the separation vector. Now we get an interesting formula called Newman's formula. So that is combining all these terms, combining all these coefficients that's in front of this phi 2, and so here this mutual inductance is all the terms here with by excluding this I1. And now if we take a closer look at this expression, we see that this expression doesn't depend on the current on any loops. So it's only a mathematical or a geometrical expression, and that involves the information how these two loops are placed in the 3D space. So as long as you know how the relative position orientation of the two loops, then you can use this formula to mathematically calculate the mutual inductance. And you don't need to even know what's the physical current running in these loops. So this M21 is a pure geometrical quantity. And you can also see that because here this is a separation vector, the magnitude. So if you replace the L1 and L2 positions, the integral doesn't change at all. So which means that the mutual inductance of from 1 to 2 is the same from 2 to 1. So now we can actually sometimes use this property to simplify our calculation. So for example, we have seen this example again before in 2041. I'll just mention briefly how this has been done. So here there are two solenoids. One is slightly larger, so it's a solenoid outside, and then there is a tiny solenoid inside this tube. So now if we apply a current into the inner solenoid, then this will produce a flux to the long solenoid, right? But the catch is that the field produced by this small solenoid is annoying. Like it's uniform inside, but it has a very complicated shape once you go outside to this solenoid. So if you want to calculate the total flux in this long solenoid, then it's an extremely complicated calculation, right? But we can actually look at this problem in a different perspective. So now, even though you run a current and want to calculate the flux through the long solenoid, that is only determined by your mutual inductance M12. But M12 is exactly the same as M21, which means that though it's hard to calculate the flux produced by current of the small solenoid, we can invert the problem and put some imaginary current into the long solenoid, and then this long solenoid produce a very nice magnetic field inside this inside the tube. So the magnetic field produced by a long solenoid inside the tube is a uniform field, and this magnetic field will produce a simple flux into this inner tube. So it's extremely easy to calculate the flux if we specify the current on the outer solenoid. So that's how we calculate the mutual inductance first. And then from the mutual inductance, we can deduce what would happen if we run a current in the small solenoid. So that's how we do it. Then the B field produced by this long solenoid is extremely simple. It's simply proportional to the current, and the number of the wraps, number of turns per unit length. And you can also double check the results in lecture 13. And now after we get the B, because the B is uniform inside, we can simply multiply the pi a squared to get the flux. And also because there are N1 times L turns in 1 unit length, then the flux per unit length is N1 times per L length is N1 times L. So the total flux through the smaller solenoid is simply proportional to pi a squared, which is the area of that small solenoid, and the N1 and N2, which is the wraps per unit length, and times the small solenoid length and the current. So from that, we can immediately write down this mutual inductance, which is the term here, excluding the current here. So now, using this mutual inductance, then if we multiply the current in this small solenoid, then that will give us the flux through the long solenoid. So we can even calculate the flux through the long solenoid without knowing the exact magnetic field produced by this small solenoid. So it's sort of a trick to help you calculate the flux or the mutual inductance. So this inductance doesn't always need to happen between two loops. So instead, we can even have an induced magnetic field on the circle itself. So imagine that I have a circle of current running in the closed loop wire. So this circle of current already produced some magnetic field, and this magnetic field already have a flux into the loop itself. So this is the term called the self-inductance. So if you try to change the current inside this loop, you will feel an EMF acting backward. So it's actually so if the inductance of that loop is huge, then it means that it's extremely hard to change the current in this loop. And say that if we have a superconducting wire, then this means that actually if we specify a current onto a superconducting loop, then this loop actually cannot change current anymore, and the current will flow in that loop forever. That's because say that if you want to increase the current, then that will produce EMF in the other direction, which balance off the current. So the total effect is that there cannot be any change of EMF on this superconducting loop, and then the flux will also be not changed, and the current cannot change at all also. But here say that it's a normal loop, and we want to calculate the inductance, the self-inductance, then we can simply use the exact same formulas. So if we introduce some sort of current, and then that must give us some corresponding flux phi. And if we calculate this flux, then the ratio of the flux over the current will give us this inductance L. So I use L here for the self-inductance. And now this EMF is simply the negative of the flux dt, where this here say that we don't change the geometry of the loop, but only vary the current. Then this L is a constant, so we can pull this L out of this differential, and that will give us this EMF equals to minus L di dt. So the unit of L is defined as henries, and now if we look at what's on the left side, it's the voltage, and on the right hand side it's the ampere per second. So if you move that to the left, that gives us second per ampere. So the total unit is volt second per ampere. Now from this, then we can have everything we need in a circuit. So for a circuit, we typically have some sort of self inductance, because in order to have a circuit, we typically need to have a closed loop, and then the current can run in this closed loop. So for any physical or realistic circuits, there must be some sort of self-inductance. It could be small, but it sometimes can be large. And you can deliberately add some self-inductance into this circuit. So for a typical circuit, we must have some sort of inductance here, and it also has some internal resistivity. And here we idealize this current, idealize everything, and say that we combine all this self-inductance into one component, and combine all this resistivity into another component, and also have the source of the voltage into one ideal component. And then this gives us the typical LR circuit. And this also has been discussed in, I'm not remembering, it could be in chapter 13 of Physics 2041 as well. So if you don't remember, you can go back to check. So then the problem here is, say that we have an ideal circuit, and like this, what happens if we turn on the switch? So that is the typical thing that you do in your daily life. Say that you switch on the light, and then that's what happens in a circuit. So after you switch on, then there will be current flowing in this loop, and now for the if you produce some current into this solenoid here, then it will produce EMF, and the EMF is what we derived earlier, is minus L times di dt. So it's proportional to this change of the current. So say that if we have a current that's building up initially, then we will introduce some EMF back into this circuit. So what this solenoid does is that it will try to counteract the EMF field. So it will try to slow down the increase of the current. So now if we write down this Ohm's law, so the EMF, the total EMF along this loop is the EMF produced by the battery, and then an additional back EMF produced by this solenoid, and that voltage must equal to IR. So now we simply need to solve this differential equation. So this is a exponential function, and now if the final solution of that current should be written here. If I plot the current, it looks like an exponential increasing function here. So what this tells us is that whenever you switch on the light actually is not turned on immediately. Actually, there is a time window that the current increase gradually, and you can see that this the rate of this current, the increase of this rate is determined by this R over L, and the time is the characteristic time it takes is L over R. So imagine that you take the limit, the inductance goes to 0, then it will be a sharp function like this, which means that if the loop doesn't have any inductance, then the current will instantly turn on. However, if somehow the L is large or the R is small, then it will take a long time to reach the desired current. Say now we have a superconductor, then what means that the R is equal to 0. So this means that actually if you connect a superconductor to a battery and with some sort of solenoid, then the energy will flow all the way to this solenoid and in building up a magnetic field, and the energy there will be a constant flow of energy from this battery to the magnetic field, and it will increasing forever without stop until all this battery power is being exhausted. Any questions? Say it again. So if you take you can try to take the R goes to 0 limit. So you can solve this equation by taking the R to 0. You should get some sort of so then if this is there, if this term is 0, then you get a differential equation that's the di dt equals to the EMF times the L. So this means that the I will increase linearly as a function of time. So Yeah. So that's only an ideal case, right? So, uh, you need the first perfect battery, and then, also you need a perfect superconductor. So, in the ideal case, then in principle, you can have a infinitely increasing current, but in reality, if there's any sort of resistivity, then eventually it will saturate. So in reality, the current must saturate somewhere. So now I don't know if you have looked at some of your chargers, or maybe your chargers to the laptop, and you might sometimes see a ring here, and sometimes it's annoying. But what this ring does is that it actually has a magnet inside, and it wraps some coils. So this actually is some sort of provides L into the circuits. So this will try to uh, delay the sudden change of a current. Say that you get a thunder strike into this socket here, and then there will be a huge spike of current, and this magnet will filter out the spike and protect your equipment. So it has some use here. So we also seen this kind of circuits in 2041. I'm just repeating it here. So now instead of having a resistor on the right hand side, we can have a capacitor here. And are you familiar with what happens if I turn on the switch and say I put a charge initially here, and what happens to the circuit? Like, can any of you predict what happens? Say if I turn on the switch and let the current flow uh, within the circuit. Okay, so I guess most of you might have already forget what happens, but this is actually some uh, typical circuits. So it's a very famous circuit, and if you do research on superconductors, you might be very familiar with this circuit. It's called LC circuit, and it's actually similar to a harmonic oscillator. So you can sort of imagine that. I'll just give you the conclusion first. So initially, the energy are stored in this capacitor, and now as you turn on this switch, there will be some current running on this loop. So the charge will flow from one side to the other side, but it cannot flow too quickly because of this solenoid. And this serves as a damping force for this capacitor's current. So the current will change slowly, and meanwhile there is a change of energy from the electric energy to the magnetic energy here. So you can see that the energy oscillates between a capacitor and a solenoid. So you can see that the electric and the magnetic energy, one is oscillating, another is also oscillating, but they are out of phase. So if you do a similar calculation, you can guess that the EMF must equal to the minus L di dt, and the EMF also equal to the Q over C. That's the, sorry, the C should be capital, and the C is the capacitance. And now we also have a relationship between I and Q, right? So here we already have a di dt. So these two combined will give us a differential second order differential equation on Q. So the Q will be having a sinusoidal oscillation, and the result is here, and the oscillation frequency is L times C. And also, if we do a differential time derivative on Q, we get the current. So the current will also oscillate in a sinusoidal way. So in the end, what we get is an oscillating current. So last, I guess that we don't have exact all the time to finish that, but I will try to mention a little bit about how to calculate the energies stored in a magnetic field. So I wonder, like, if you still remember the expressions for the energy stored in an electric field. From we actually start from the to start the derivation of the electric field from the deriving the work stored in a capacitor, which is, if you still remember, is 1/2 the capacitance times V squared. And here we do the exact same thing. So when we calculate the energy stored in a capacitor, we increase the voltage from 0 to the desired voltage V, and then we do a integration of I times we do the integration of the charge Q times the V. And so the total work done is the total work done needed by moving the charge Q from one side of the capacitor to the other side of the capacitor. Here the result is the derivation is exactly similar, so we can calculate the energy in a magnetic field by slowly ramping up the current in the loop from a small value to the value desired I. And that will give us all the works done over the time. So here the dW dt equals to the minus the EMF times the current, and the EMF is also related to the minus L di dt. So on the right hand side, it's a function that's only on I, and now if we integrate both sides, that gives us the work equals to 1/2 of self-inductance times the I squared. This equation is exactly or is similar to the energy stored in a capacitor, and it actually doesn't depend on how long we increase the current, but it only depends on the geometry of the loop and the final current running in the loop. So you can sort of see the mapping, right? And now we also have alternative expressions for the energies. We will discuss this later.